Good afternoon and welcome to Learn from Home from WVIA. My name is Dr. Colleen Ruths and I teach at Shikellamy High School where I teach computer science and physics. And I'm going to share to you some phenomena around good vibrations and help explain why good vibrations lead to really good music and not just the kind that the Beach Boys play. So first thing I'm going to show you is a phenomenon with a Chinese bowl. So I have it down here on the ground. Okay, so this Chinese bowl, I have some water in it, and I'm gonna wet my hands because that's part of this whole process, and we're gonna try to create some good vibrations in here. So if you've noticed that there's a pattern that gets set up by these vibrations. So there's a place where the vibrations are really big. You can see it's kind of marked actually here in the in the bowl itself. And then there's places where there is no vibrations that show up, or no. All right. So my question to you is, besides what I pointed out to you, what else do you notice? And can you explain what you are seeing in detail? So by the end of this segment, we'll come back to this, and I hope you have an answer for me.
So hi, we came back inside because I have to show you everything else from the inside here. But remember, we saw those water droplets popping up out of the Chinese bowl. And I was curious as to what you thought about that and what you noticed with that phenomenon. And can you explain that? Okay, good vibrations, how vibrations lead to resonance, and which then leads to music. So before we get too far into my explanation, I'd like you to gather a couple of things. So we're going to do a vibration experiment to help you understand the relationships that happens with those. So the first thing you're going to need is a pendulum. So like a long necklace will do. And you're going to need a stopwatch. And finally, you're going to need a ruler. So those are the things that you're going to need. So a pendulum, a stopwatch, and a ruler. So here's what we're going to learn today. First off, we're going to start with some demonstrations on vibrations to see what you know. Then we're going to talk about what resonance is, how the energy gets input, how that leads to vibrations, and how that then the output resonance, and then how that resonance gives us music. So we're going to be learning about the phenomenon of sound. Okay, so you did see the Chinese water bowl, and so now I'm going to show you a water glass. Okay, so not a water glass, but a wine glass. So this is a wine glass. Listen. So you can, if you have a nice wine glass at home, you can do this same trick or this phenomenon with them. So you just need some water, and you put water in the wine glass. Okay. And then, very similar to what I was doing with the bowl, if you, and there's a tricky little spot, you can get the wine glass to hum. All right, so notice that when I hit it and when I put in energy this way, we hear the same sound, right? We're going to talk about what that means in a bit. So can you explain what is happening there? All right, so are you ready for your experiment? So we're going to try to at least understand what affects a pendulum, and we're going to then use that to help us understand what goes on with sound then. So I have a pendulum. Like I said, a good old necklace will help. And so you want it to be able to swing. And you notice, like when I start it, it continues to swing for a long time. So a period of a pendulum is how long it takes for it to go back and forth. So 1 period, 2 periods, 3 periods, 4 periods. So what I want you to do is get your own pendulum and try this experiment. And you're going to measure the length of the pendulum, and then you're going to measure how long it takes for one period. Now, usually it's really hard to do a really good job with a stopwatch to measure just one period. So I would recommend measuring 10 periods. Okay, so remember, we're going to time a pendulum, and you can use the stopwatch on your phone to help with that. And we're going to measure it. So I'm going to try to do one. It's best if you have a lab partner. Lab partner is always fun to have. And you should do your measurement of your pendulum from where you're holding it, or I recommend leaning it over a cabinet, to the center of the mass. Okay, so this is a 12 centimeter pendulum. And I have my stopwatch ready. So I'm going to pull it back and start my stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so about 6.7 seconds. Okay, now every good scientist will take more than one reading at that. Okay, but on a data table, you can then, so we said it was 12 centimeters. So 1.2, that's in meters. And I said that was 6.7, that was for 10 cycles. So 6.7 seconds for 10 cycles. So divide that by 10 to get it for one cycle. So that is 0.67 seconds. Okay, so we can do another one together, and then I want you to try this at home and then see if you can find out what relationship this is. So now we'll do the long one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that was a lot longer. And again, I would recommend doing it a couple of times to make sure you get good data, because especially me flipping back and forth here. So, oh, I didn't measure the length of that. So this is a, we're going to say 29 centimeters. So 29 centimeters is 0.29. And we said that was 11.9 seconds. So I'm dividing that by 10 because that was 10 cycles. So that is 1.109. And again, these are seconds. So there you go. So what you should do is try to do about 10 different lengths in there and see what shape of a graph you get. We'll come back to that perhaps. But what I want you to see is that as the length gets, what you should see with just these two data points, right? As the length gets longer, the period gets longer. All right, that's called a direct relationship. If you do some more analysis with it, you'll see it's not a completely direct. There's a little bit difference in that. But in general, as one gets longer, the other one gets longer. Okay, so that is our understanding of a period and a vibration. So I don't know if you noticed though, when I was swinging this, it didn't stay swinging the whole time, right? If I wanted this to be a permanent vibration and swinging, I would have to put energy into it by giving it a push every now and then. Think of being on the swing set, right? When you get on the swing set, in order to keep on going, you either have to pump your legs or you have to have someone push you. All right, so I'm using energy and I'm putting energy into the vibration to keep the vibration going. Now, it's an important when I add the energy, right? If I tried to add the energy here, it wouldn't swing the same as if I wait until it comes back and I add the energy at the same time. All right? So that's a very important thing to understand, is that I have to wait to add energy that goes along with the vibration. If I add the energy differently, I actually begin to stop that. All right? So what we have seen so far is that this is a vibrating particle. So that is an example of a vibration, and that when we add energy to it, it keeps on going. And so now I'm about to head over into some vocabulary that we can begin talking about sounds and vibrations and how that pendulum is very similar to sound. So the vibration experiment, again, the materials. So what is the relationship between the period and length of the pendulum? And what we found was that as the length gets smaller, the period gets smaller as well. Okay, so here's some vocabulary to help us along the way. So the period of the pendulum, right? We just said that was the length of the time for one cycle to occur. So the back and the forth of a pendulum or a vibration going back and forth. So the period and the frequency are direct opposites, or we'd call them inverse relationship. So if a period is the length of time for one cycle, the frequency is the number of cycles in a second. Period is seconds per cycle, and frequency is cycles per second. So they are reversed of each other. So that's an important thing to understand, because remember, with the pendulum, period, as it got shorter, the period got shorter as well. But it's going to be the inverse of that. So when it gets shorter, the frequency gets larger because there are more vibrations in a second. So in a long one, as the length gets longer, the frequency gets shorter. There aren't as many cycles in a second. So that is an inverse relationship. So period and length is a direct relationship. One gets bigger, the other one gets bigger. Length and frequency is the opposite. As the length gets longer, the frequency gets smaller. Okay, so resonance then is the tendency of a system to vibrate at a specific frequency. And so the pendulum, in some ways, that's the resonance of it, right? When I change the length of it, I change its resonance, its specific frequency that it vibrates at. So you can see that. And then the amplitude is the size of the vibration. So that's a big amplitude. But if you will take it and measure that, it does not change the length of the period. So if I make it a small amplitude, that's going to be the same period as a large amplitude. So amplitude has no relationship to the period. Okay, so understanding the phenomenon behind a pendulum will help you better understand the phenomenon of sound using those ideas of frequency, resonance, and amplitude. Okay, so resonance is the tendency of a system to vibrate at a specific frequency. So that has a specific frequency that we hear, and that is because that resonates at that frequency. I can change its resonance, or the frequency that it vibrates, by changing its length. So that is a different sound than we just had a few seconds ago. So notice I've changed the length, and therefore I have changed the frequency. Resonance can build up in an object. So if an object resonates at the same frequency, it can build up into that vibrating object until it breaks. So you've probably all famously seen someone break a wine glass with their voice. And I am not doing that today. I'm sorry to tell you that that is not part of my plan or my specialty. But you can watch it on YouTube. They did it on Mythbusters and a couple of other things. So you can definitely watch it. Pendulum swinging is an example of resonance. I'm going to show you now a spring that I have here. And the spring can show us some resonance as well. Here's a spring I have attached to the wall. And notice when I drive it with a certain amount of frequency, I can get it to resonate where it reflects off the wall on the other side. There you go. And you can see a place where it reflects here and it comes back. And so what has happened is I've sent a wave down and it reflects off the wall and it's coming back and it hits the wave, the next wave that I've hit at the same time. And they constructively create a big node here, and the ends are called antinodes. So that, notice how much energy it took me to do that. Here you can see a node here in the center. That is a deconstructive. So constructive interference here, deconstructive interference here because of the wave vibrating, reflecting off the wall. And then if I add a lot of energy, I can get like 3 in there. Okay, so again, that spring is resonating with different frequencies depending on how much energy I put into it. Here is something that you can make at home. This is called a resonance circles. And so all I did is use a piece of cardstock. If you have some, construction paper will work as well. And then you cut just different lengths of circles. And so I'm going to try to show this to you. So when I go back and forth slowly, you can see that the big circles resonate, but the other ones don't move so much. If I add more energy, I can get the little circles to vibrate, but then the big ones stop. So everything resonates at its own frequency based upon how much energy. And get the little ones to, it's really hard to get the little ones to vibrate. But if I add some thought, and it seems like the little ones and these have a similar frequency that they'll vibrate at, but again, these don't as much. So vibrate, these are called resonance circles, and you could try to make a whole line of them if you wanted to and see how that works. So resonance in the pendulum, it resonates at different frequencies depending upon how long it is. Resonance in the spring, it vibrates at different frequencies depending upon how much energy I put into it. Resonance in the wine glass based upon how much water is in it, right? And then the resonance circles. So the next thing I'm going to show you is something that was engineered that resonated, and it resonated so much that it actually broke. So let me share a video with you. Okay, so what I'm showing you here is an example of a resonance that went way overboard. So this is Tacoma Bridge. This was built in 1939, opened in 1939. You can see how nice it looks. Lots of people walking across it. Notice how skinny it is. However, now you should notice that it is vibrating. It is resonating. You can almost see a whole length, a wavelength in there. So it's resonating with the wind. So you can see the vibrations that are happening with it. Now, unfortunately, what happens is that they had to close the bridge, but eventually the resonance got so big and so bad that the bridge collapses. So here is the bridge falling apart and into the water. Okay, so we talked about the resonance, we talked about the spring, and so how does that all affect with music? Well, different musical instruments will resonate at different pitches, and that'll give us different sounds. And just like the pendulum, it's based upon the length. So here's a xylophone, and depending on how long it is, you will get different pitches. So what do you think this one is? This one is shorter. So what happens to the frequency when something is shorter? What will you expect to hear? Okay. And how about this one? So it's higher. Yeah. Okay. So that was a pipe, or that was a steel, and the nodes were on the ends. If you have an open pipe, though, the nodes are not on the ends. That's going to be an antinode, a place where the wavelength is separate. So you've got that sound. So this one is shorter. What do you think it's going to sound like compared to this one? Do you have a guess? So a whistle acts the same way, right? A whistle. When I make it long, you hear a lower pitch. And when I make it short, you hear a higher pitch. So in music, pitch and frequency are the same. This is an Egyptian guitar of some sorts. I don't claim to play it, but what I want to show you is that it also has vibrations in it. Now these two are the same length. These two strings are the same length. So that's a bit confusing because if they're the same length, why aren't they the same pitch? Well, there is one other thing that contributes to the pitch, and that is the tension in the object, the string. So if I tighten this, by increasing the tension, I increase the sound that I hear. So despite the fact that these two are the same length, because they have different tensions on them, you will get different sounds from them. So do you resonate? What do you think? Well, the answer is probably you do. You've been someplace where the music's really loud and you feel your stomach or something inside moving you. You are resonating with that beat of music. And does your house resonate? I bet all of you have been in the house when a truck or a train goes by and you can hear the windows vibrate in your house. So resonance is what almost every object resonates. So it's a phenomenon that goes all the way from the universe all the way down to the atomic scale. And so understanding how frequencies and vibrations work is really important to being able to understand and predict how the world works. Okay? So, so going back to the Chinese pot, where you saw those vibrations. Can you now explain some of the phenomenon you saw in there? Let's go back outside and see what else you can tell me.
Yay!
And so, my little physicist, you have learned a lot of new words today that you can apply to all sorts of phenomenon that you see every day. So remember, frequency, how often a vibration happens, vibrations. Resonance is a forced frequency that happens and everything resonates at its own frequency, and sometimes multiple frequencies. And finally, how frequencies and resonance give you pitches and music. So good vibrations lead to good music. Thank you for joining me today at Learn from Home with VIA. Have a great afternoon.